Of all the planets in our solar system, scattered across hundreds of millions of miles, a single blue-white planet has demonstrated the incredibly complex ability to support life.
When we first think about astronomy, the things that come to mind are those exotic objects that are far from the surface of planet Earth. But the planets in our own solar system are part of the astronomical universe too. And if you're studying those planets and want to understand how they work, well, it's very handy to have a planet under your own feet. Places like Mars and Venus, then, that are somewhat like the Earth, are a bit more comprehensible when we examine the similarities and the differences from them to Earth and back again. Well, Ganymede, one of the largest satellites of the planet Jupiter, is now known to experience plate tectonic activity on its surface. And Venus possibly has evidence for the same kind of thing. Plate tectonics, however, were first understood here on the Earth, for the Earth has that same kind of thing occurring to it. So now we actually measure one of the effects of plate tectonics, continental drift, by satellite from outer space. So the Earth helps us better understand the planets and their moons. And by studying the planets and their moons, we can better understand our own planet Earth.
According to the theory of plate tectonics, the Earth's surface consists of moving yet rigid slabs of rock. The theory suggests that there are about a dozen giant plates that form the Earth's outer shell. The plates differ in size and shape and carry the continents and oceans alike. And they literally float on the much denser but somewhat molten rock that lies below, much like the skin on chocolate pudding. The plates move back and forth, sometimes colliding, sometimes sliding under one another, forming the deep ocean trenches or spawning volcanic activity on land. They can also crumple together to form mountain ranges. And when they scrape against each other in a parallel direction, the result can range from a mild tremor to a catastrophic earthquake. Actually, the concept of plate tectonics began to evolve hundreds of years ago when explorers first charted the margins of the continents. In 1620, Sir Francis Bacon studied some of these coastlines and suggested that their apparent congruence might be more than coincidence. In 1858, Antonio Snyder developed a diagram to illustrate his theory that the continents were once united. He based his claim on the striking similarity between fossil plants in Europe and in North America. Then, at the beginning of the 20th century, Frank Taylor and Howard Baker presented separate but closely related theories based on the alignment of the mountain ranges on opposite sides of the Atlantic. They claimed that these mountains were once a continuous chain that was broken up by large-scale movements of the continents. So by the early part of the 20th century, The notion that the continents may not have always been in their present locations was attracting increased attention.
The idea was never seriously considered, though, until Alfred Wegener, a meteorologist and geographer working in Vienna, Berlin, and Graz in Germany and Austria, proposed quite seriously the idea in 1911 that North and South America had been snuggled up across the Atlantic Ocean to Europe and Africa. His idea was not accepted by geologists at the time. There were many arguments put forward opposing the so-called idea of an initial supercontinent, Pangaea it was called. But that was, of course, only half of Wegener's hypothesis. His hypothesis was the continents had been together, and now, at some stage, they broke apart and drifted away from one another. The theory was called continental drift for obvious reasons, and the actual rupture and drifting apart would lead to the apparent congruency of the parts of a puzzle. We look at this today, and we see very clearly that the eastern and western hemispheric continents do mesh across the Atlantic Ocean. Moreover, there is an amazing ridge that runs down the length of the Atlantic called the Mid-Atlantic Ridge. It's halfway distant to both continents, eastern and western hemispheric continents, and it too exactly, faithfully outlines the coastline of both, shall we say, South America and Africa and North America and Europe. So this ridge is in fact a divergent plate boundary, as we now know, and it represents the original fracture zone where Pangaea, this ancient continent, split up on the order of 180 or 200 million years ago. And North America and South America drifted relatively westward as new plate was formed in the Atlantic Ocean, and the eastern hemispheric continents, Africa and Asia, Europe too, all drifted coherently relatively eastward. That's the idea of continental drift. There are many other aspects of it. Australia, India, Antarctica are also part of it, and they were whizzing around at the same time.
Plate tectonics and continental drift may help explain what's happening on the Earth's surface. And so these studies may allow us to understand a little bit better the Earth as a planet. But there's another reason for trying to understand well the Earth's behavior and motions. This piece of interplanetary rock is more than just our home. It's our observation platform. And the information that we get from the distant stars and galaxies is affected by the motions of the Earth as well as some aspects of its own composition. That light from the distant stars has to pass through our atmosphere. And the effects of that atmosphere, as well as the effects of the motion of the Earth itself, must be compensated for when we analyze our data. So this atmosphere, this thin gauze of gases that's so salutary to our health, also does interfere with our astronomical research. But we can investigate the Earth and understand how these things do affect our observations, and so take them into account. It's well, then, for astronomers, every once in a while, to pay some attention to Mother Earth.
The Earth is the third planet from the Sun, and it belongs to the inner terrestrial group of planets, Mercury, Venus, Earth, and Mars. They're called terrestrials because they're all similar to the Earth, heavy, rocky solids. Although the Earth appears to be a perfect sphere at first glance, it's actually an oblate spheroid, which means that the planet is flattened slightly at the poles and has a slight bulge at the equator. So the equatorial diameter of the Earth is slightly larger than its polar diameter. This flattening effect is primarily due to the centrifugal force created by the Earth's rotation. In addition, precise satellite measurements of the shape of the Earth reveal that it actually is slightly pear-shaped, although the effect is greatly exaggerated here. The equatorial diameter of the Earth is 12,756 kilometers. In comparison, The Earth's diameter is about 3 times that of the smallest planet, Mercury, and about 11 times smaller than that of the largest planet, Jupiter. The mass of the Earth is 6 times 10 to the 27th grams. In comparison, it's about 20 times more massive than Mercury and about 300 times less massive than Jupiter. The density of the Earth is measured as being 5.5 grams per cubic centimeter, which means that the average density of the entire planet is about 5.5 times the density of water. So there's obviously a great deal of solid material, which is much more dense than water. The Earth makes one complete rotation on its axis every 24 hours, which accounts for the length of our day. And it makes a complete revolution around the sun in 365 1/4 days, which we measure as 1 year. As the Earth revolves around the sun, a number of factors result in the seasonal changes which we experience throughout the year. To begin with, the Earth's spin axis isn't perfectly vertical in relation to the plane of its orbit. It tilts by about 23.5 degrees. So as the Earth moves around the sun, the northern and southern hemispheres are alternately tilted toward and away from the sun. And when a point on Earth is tilted away from the sun, the sunlight strikes the surface at a greater angle, which results in a cooler temperature. As far as the seasons are concerned, there are 4 distinct positions which occur along the Earth's orbit: the winter and summer solstice and the spring and autumnal equinox. The dates associated with those 4 points in the Earth's orbit are traditionally recognized as the start of their respective season. Usually December 22nd, March 21st, June 22nd, and September 23rd. For the northern hemisphere observer, the sun reaches its highest point in the sky at the summer solstice and its lowest point in the sky at the winter solstice. So during the summer, the sun follows a higher arc across the sky, creating a longer, warmer day than during the winter, when the sun moves across the sky in a more shallow arc, creating shorter, cooler days.
Instruments like these allow us to understand what the inside of the Earth is really like. This is a seismograph, and it's able to detect the waves that pass through the Earth. It allows us then to understand something about earthquakes, when and where they occur, and also how strong they are. But also by carefully studying the measurements of seismic waves, we can gain some understanding about the materials through which those waves must pass, the materials that make up the internal structure of the Earth.
The lithosphere, this relates to the plates in plate tectonics.
Dr. James Whitcomb is a senior research fellow at the California Institute of Technology and is responsible for Caltech's seismic array in Southern California for earthquake monitoring.
My major interest is in seismology, and a good portion of our knowledge about the inside of the Earth comes from seismology. That is, studying the way the sound waves that are generated by earthquakes propagate through the interior of the Earth. The velocity that these waves propagate, or the speed that they propagate through the interior of the Earth, tells us a lot about the mineral composition and the layering, because we can take a rock and put it in the laboratory and measure its velocity. So also under very high pressures we can measure its velocity, so we can compare velocities that we get in the laboratory to what we measure inside the Earth. And by all of these diverse clues, we can put together a picture of what's in the Earth by looking at rocks that are on the surface and by inference. Planet Earth is a very complex structure, but one can describe it in rather general terms. The upper part of the Earth is composed of the crust, and it's composed mainly of feldspars. The crust varies in thickness from about 20 kilometers thick to sometimes 60 kilometers thick under the deepest mountain ranges. Underneath the crust, going all the way to the core, is what we call the Earth's mantle. The mantle is assembled of much more dense material, probably olivines and pyroxenes. They're the favorite candidates of geologists. And it goes all the way down to a depth of about 3,000 kilometers deep, or a radius of 3,200 kilometers radius. Below the Earth's mantle is the Earth's core. Now that has a tremendously different chemical composition. It's mostly composed of iron with some nickel and other elements, perhaps sulfur, perhaps silicon. This is a matter of debate still among geophysicists. But the core itself also has an inner structure called the inner core. And this is probably another phase of iron. It's probably iron that has become solid again as opposed to the liquid outer core, or liquid iron. The intense pressures that the inner core experience probably solidify the iron again, even though it's very hot, to where this behaves as a solid. And the inner core has a radius of about 1,200 kilometers.
One of the most striking features of any view of the Earth from space is that almost 75% of the planet's surface is covered with life-supporting water. The planet's water, in all forms, is called the hydrosphere. The liquid phase of the hydrosphere includes the rains, the oceans, rivers, and lakes. The solid phase includes the ice caps, glaciers, and snow caps. And the gaseous phase is found primarily in the atmosphere, where the water condenses into clouds. And another important aspect of the hydrosphere is the hydrological or water cycle. The warmth from the sun evaporates water from the oceans and lakes. The winds carry the moisture over the land, where it condenses and falls as rain, then runs off into the oceans and lakes, forming a continuous cycle. But of all the environmental spheres of the Earth, there's no question that it's the atmosphere that has the greatest day-to-day influence in our lives. In fact, it's exactly this life-giving layer of gases which allows the abundance of life on Earth to have formed in the first place and to continue to survive. The atmosphere provides the very air that we breathe. It absorbs harmful radiation from the sun, and it acts as a blanket of insulation which equalizes the night and day temperatures by trapping the life-supporting warmth from the sun. If the Earth were the size of an apple, then the atmosphere would be no thicker than the peel. But even so, the atmosphere extends for hundreds of kilometers above the surface of the Earth, although the various layers of the atmosphere can't be clearly separated by distances from the surface. A number of distinct characteristics have been discovered about each layer. The bottom layer is the troposphere. This is where the noticeable, sometimes violent changes in our weather occur. This is also the densest concentration of the life-giving gases which make up the air we breathe. In fact, about 99% of the atmosphere is concentrated below 35 kilometers from the surface. The next layer is the stratosphere. It's in this area that the ozone layer occurs, to effectively screen out most of the harmful ultraviolet radiation from the sun. Above the stratosphere is the mesosphere. This is normally the level of the atmosphere where meteors can be seen. The next layer is the thermosphere. This is the level which filters out most of the dangerous X-rays and gamma rays from the sun. The temperatures in the thermosphere climb steadily to extremely hot values. As we approach the exosphere, the uppermost layer of the atmosphere, which is hundreds of kilometers above sea level. Also, it's in the upper two levels of the atmosphere that the upper and lower aurora, or northern and southern lights, occur. The auroral displays are one of the most mysterious and strikingly beautiful events in our environment. Their intricate, ever-changing form and their marvelously subtle colors are difficult to capture, even in highly specialized photographic records, which can only provide a tantalizing hint of the actual event. Scientists believe that violent solar disturbances send streams of charged particles into space. Near the Earth, the particles are deflected by its magnetic field. They collide with atoms and molecules in our atmosphere and produce the magnificent auroral displays. During the appearance of an aurora, a wide range of strange and often misunderstood disturbances can occur. Telephone transmissions and long-distance radio communications can be disrupted. Radio transmissions of photographs can be distorted or even blacked out. Although not yet completely understood, auroral displays have fascinated observers for thousands of years. Other than contributing to the aurora, the Earth's magnetosphere is a highly complex system. In 1958, American physicist James Van Allen discovered the massive Van Allen belts, which encircle the entire planet. These two donut-shaped regions reach out to thousands of miles from the surface of the Earth. In essence, the Earth's magnetic field presents an obstacle to the flow of the solar winds from the sun, creating a massive bow shock wave. The trapped charged particles are concentrated in the inner and outer Van Allen belts. Very simply, the Van Allen belts can be considered as the areas where the radiation emanating from the sun is most intense.
We don't really feel the Earth turning. We can't sense that motion, but it is possible to prove that it does turn. And in fact, Jean Foucault did prove that in the middle of the 19th century with a device just like this, a Foucault pendulum, which he invented. The pendulum is just a heavy weight attached, suspended by a long wire, and it has a mechanism which permits it to keep swinging back and forth. The pendulum would swing back and forth in the same direction if it were not acted upon by any other forces. And in fact, the only force that pulls on the pendulum is the force of gravity, just due to the Earth. However, if we watch the pendulum for a while, we see that it appears to change its direction of swing and gradually knocks these pegs over. The pegs actually are what's moving, not the pendulum. The pendulum continues to swing back and forth in the exact same direction in which we started it, because nothing else is affecting it. But the Earth is turning underneath it, and the Earth turns those pegs into the path of the pendulum, and so they're knocked over. It's easier to visualize this, I suppose, if we imagine one of these penduli on top of the Earth, say at the North Pole. You put the pendulum up there and let it swing back and forth, and it's easy to see how the Earth would turn underneath it, and in fact, make the pendulum appear to change its direction of swing through a complete cycle in 24 hours. At the equator, however, the pendulum will never go through a complete cycle. And from the pole to the equator, it takes a longer and longer period of time for the entire cycle to occur. This then is one of the primary demonstrations of the fact that the Earth does really turn.
See, rotation is the spin about the axis. Revolution is orbital motion, the Earth's revolution around the sun. One consequence of the Earth's revolution, although it's not obvious why, is the fact that we have seasons on the Earth. Another consequence of the Earth's revolution, which is obvious to astronomers, is the fact that if my left hand is the sun and, well, here's the Earth, the sun is over here, then, let's see, this would be winter in the northern hemisphere. And so if we wanted to go out and observe at night, this would be the nighttime side of the Earth. It would be dark because the sun is illuminating this side of the Earth. And the constellations that we would observe in the winter are off in that direction in space. However, all those consequences could be explained by a sun and a celestial sphere, stars, that went around a stationary Earth once a year. So the question is, how do we prove that the Earth goes around the sun and not that the sun goes around the Earth? One of the simplest ways to prove this is using the concept of stellar parallax. Parallax is a concept that we have all used because it's the concept that gives us our depth perception. It's the phenomena which, if I hold the pencil up and I look at it with my right eye and then with my left eye and then back and forth, the pencil seems to jump back and forth relative to the background. That's parallax. Our nearby object becomes a nearby star, and our distant objects become the background stars. And the idea is, if my left hand is the sun and my right hand is the Earth, then if the Earth is going around the sun, then we should observe the nearby stars to shift back and forth relative to the more distant stars. As the Earth moves over to this side of the orbit and then back to this side, we should observe the stars to slightly change their direction. On the other hand, if the Earth is stationary, is fixed in space, and the sun is going around the Earth, then we should not observe any parallax. when we look at the nearby stars relative to the background stars. But that we consider to be a proof that the Earth goes around the sun, because there's no other explanation for why the nearby stars should shift. Another motion of the Earth, which is important to understand, but which is very subtle, is not obvious to the average person, is a phenomenon called precession. Not precision, but precession. Now we say to a first approximation that as the Earth rotates, it keeps its spin axis always pointed in the direction of Polaris. Not exactly, but close to Polaris. And that's why Polaris is the pole star. It's always seen above the pole. In point of fact, that's not exactly true. The Earth's spin axis does not always point toward Polaris. In fact, what it's doing is very gradually, the Earth's axis is changing its direction in space. Maybe if we just use a pencil to represent the spin axis of the Earth, it's precessing. It's describing a cone in space. Now, this is a very slow effect. It takes 26,000 years to go once around the cone.
The fourth motion of the Earth is not at all obvious to an earthly observer. The Sun is a member of the Milky Way, and that galaxy has several 100 billion stars. The stars in the galaxy move around like a pinwheel, and the Sun moves also. As the Sun moves, it carries the planets along with it. The Sun moves between 200 and 300 kilometers per second around the galaxy. Even at that great speed, it takes the Sun 200 million years to make one revolution of the galaxy. Although the astronomer may spend a lifetime examining the myriad components of the universe, objects that span countless millions of light years, the accuracy of that study depends upon a thorough understanding of the observing platform which we all share, the planet Earth.